Hello everyone. Thank you for coming to listen to my talk. I'm Gangmuk Lim from UNIST, and this work is about approximate quantile for data center telemetry monitoring. It is collaborated with UNIST, Microsoft Research, Oracle, and Facebook. Cloud data center is now everywhere. It is well known that 90% of companies are on the cloud, and cloud data centers will process 94% of workloads in coming 2021. As a result, it is very critical to provide reliable data center more and more. This is a high-level flow of a reliable data center. Data center monitoring system measures various key performance indicators and perform crash detection, and if any crash is detected, it takes a recovery action. All these pipelines should be done in timely manner. To satisfy this requirement, it is common to practice streaming analytics. Streaming analytics is based on different types of operators, and in this paper, we will focus on quantile operator, which is widely used to detect normal and abnormal behavior for the monitor system. However, by nature, quantile operation is resource intensive since it has to keep all data points in sorted order. As a way of solution, we consider to apply approximate quantile rather than calculate exact quantile operation. We propose a new quantile approximation methodology named AOMG with following two contributions. First, we are overall providing better approximation for several important performance metrics. Second, we bring out a new accuracy metric for quantile approximation customized for data center monitored use case. That accuracy metric is value error. It is different from traditional accuracy metric, which is rank error. In the next few slides, I will show you why the value error is more important than the rank error. To explain it, let me give you a real example for network telemetry monitoring. Microsoft Ping Mesh. This is network latency measurement and analysis system for Microsoft large-scale data center. The purpose of this system is to locate the network reachability issues in large-scale data center. Using high quantiles such as 0.99 quantile, Ping Mesh draws path-to-path pairwise latency heat map to visualize network condition. Green one indicates low latency pair, and red one indicates high latency pair. Left figure shows a red cross pattern, and it tells there is network problem within a packet. And right one shows a pattern having green box in the diagonal region, and it tells there is no network issue within packet, but cross packet. As you can see, this visualization is very helpful to see where the network issue is. And actually in practice, it is utilized by network managing team, developers, and customers to check regularly if the network is fine. Therefore, it is very important to get accurate quantile approximation that is close to exact quantile value to draw heat map correctly. In order to estimate quantiles accurately, we will take telemetry data's underlying distribution into account. This blue box is corresponding to non-high quantile, and this part has many recurring values. The red box is corresponding to high quantile, and this part has substantial skewness. Under this distribution, low rank error doesn't guarantee low value error always. This graph shows impact of a rank error. R is the rank error of each quantile, and 0.02 absolute means 2% of rank error. And you can see 2% of rank error indicated by R plus minus 2K. At 0.5 quantile, here in blue box on the right side, 2% of low rank error leads to 2% of low value error successfully. However, at 0.99 quantile, 2% of rank error goes to unacceptably huge value error. This is because they have low data density in the tail part and its distribution has long tail. Let me introduce details of AUMG method. It has two parts. One is for non-high quantile, and the other is for high quantile. And high quantile is divided into two different techniques. Let's look at the non-high quantile part first. The key of efficient non-high quantile approximation is exploiting self-similarity in non-high quantile. If there is self-similarity, data distributions across different time frames are similar. So their calculated medians will similar each other across time frame. With this observation, we can get accurate quantile approximation using relatively simple two-level hierarchical method. Before explaining the method, let me define some terminologies first. There's a window, and you want to estimate the quantile of this window. And this one window consists of a number of sub-windows. In this method, approximation is calculated by getting the exact quantile from each sub-window in the first level and applying mean function in the second level. After one time step, the oldest sub-window will be discarded and the summary of new window will be added. This relatively simple method shows high accuracy for non-high quantile thanks to self-similarity. But there are two complementary cases that previous method doesn't work. They're corresponding to calculate very high quantiles. And the first case is statistical inefficiency. Statistical inefficiency happens when there's not enough data point in each sub-window for calculating given quantile. For instance, when the sub-window contains 1,000 data point and you want to calculate 0.39 quantile, then you end up with relying only on two largest values, which is statistically not robust. Second case is bursty tail. Bursty tail occurs when there is high skewness of large value in a window. So one or two sub-window has almost all the largest value of a window. For each case, we're proposing two different techniques exploiting raw data points. To tackle statistical inefficiency, top K merging caches largest value from each sub-window. Caching largest value from each sub-window lets you have enough largest value to calculate given high quantile. And the reason this method can work is that large values are likely to be distributed across sub-window. In the end, you merge them and answer query quantile. To handle bursty tail, we perform sample K merging, and sample K merging does interval sampling from each sub-window to capture the distribution of largest value of a window. This example shows sampling half of largest values. But the problem here is we cannot just beautifully select bursty tail sub-window and only does sampling from it. And here's the reason. Existing bursty tail can exceed the window, or a new bursty tail sub-window can join a window. And also after existing bursty tail exceed a window, a new bursty tail can appear suddenly in the middle of a window. And it can happen because bursty tail is relative to other neighboring sub-windows. Because of this unpredictability of burst tail, we have to do sampling from all sub-windows. And in the end, you merge and answer target quantile. Now we need to select the right technique among proposed ones at the runtime. First, when there is distinctive distribution in a sub-window from adjusted one, then it choose sample k-merging. And if not, it checks whether there is enough data point in sub-window compared to given query quantile. And if it is not, it takes top k-merging. And if you have enough data, then you just use simple Nonhigh quantile method. Let's see the evaluation. We evaluate AUMG. We implemented AUMG on Trill streaming analysis engine and run these 4 different query quantile using Microsoft Ping Mesh dataset. And we compare AUMG with 3 different rank error based methods. Let's look at the accuracy first. For the figure, x-axis shows 4 different target quantiles, and y-axis shows the rank error for the left one, and the value error for the right one. So the lower is the better. As you can see, the left graph, all competing policies provide lower rank error successfully, satisfying their design objective. And we find that AUMG is also delivering low rank error. However, as you can see on the right figure, there is a clear difference in delivering very high quantile. Only AUMG successfully bound 0.39 quantile, and except for AUMG, all other methods fail to bound value error below 5% for 0.39 quantile. And let's move to the throughput comparison. We compare AUMG with CMQS and exact quantile. The reason we pick CMQS here because it has the highest throughput among rank error-based methods. X-axis shows the different policies, and y-axis shows throughput, and the unit is million data points per second, so higher is the better. Also, we put variation on epsilon for CMQS to look at a range of rank approximation bound. CMQS has a clear trade-off between throughput and accuracy. When setting the epsilon low, it guarantees low rank error. However, it becomes too slow. When setting epsilon high, it shows relatively high throughput, but in that case, you have to sacrifice accuracy. On the other hand, AUMG achieves the highest throughput, but also keeping value error low. This shows the effect of top k-merging technique. X-axis shows different small size sub-window, and y-axis shows value error, so lower is better. And the fraction defines how many largest data point you will cache. And with top k-merging technique, AUMG successfully bounds value error around or below 5% for all appearing small size of sub-window. This graph shows the effect of sample k-merging. When there is burst tail in a window, x-axis, when there is a burst tail in a window, and x-axis shows different sampling frequency, here represented as fraction. Zero fraction indicates AUMG does approximation without sampling. And apparently, this zero fraction results in very large value error. But AUMG achieves low value error by sampling only 10% of large value for 0.99 quantile and 50% sampling of large value for 0.39 quantile. So we present AUMG, new approximation quantiles, for data center telemetry monitoring. AOMG utilizes online data distribution with new accuracy metric. It delivers high performance, low value error quantile approximation for various datasets with wide range of window size setting. This is it, and thank you for your listening. For more detailed information, please refer to our full version paper in archive.